Hey all, Rusty Rob here. Hope you've had a good weekend. So just quickly take you through that third problem in the round one of Hacker Cup this weekend. And so we'll be using Rust and we'll be finding the convex hull and then doing Dijkstra's quickly. So let's get into that. So the first problem, you got a bunch of houses. You got to make your way from the leftmost house to the rightmost house and minimize the cost. There's a few different restrictions and there's a few different ways of getting the cost between houses, but I won't worry too much about that. There's another restriction where every house you visit has to be in its own half plane, and that essentially means you only consider points on the outside, and that limits the number of points quite a bit because there's about 100 test cases or 200 test cases, and each one has potentially 1,000,000 points. But by the time we do the convex hull, we're down to maybe 35,000 points or something on the outside. So that makes an n squared algorithm doable. So then we can kind of do an n squared Dijkstra's, which is just fast enough. It takes about 20 seconds in Rust. Let's just run that. So if I time this, so you can see case 7, 8, 9, and 10 have quite a few points. And then it goes a bit quicker towards the end. Cool. So that was 26 seconds. Yeah, so to get the convex hull, you sort the points by x and then by y. So I guess this would be point 0, 1, 2, 3, 4, 5, 6, and 7. And then maybe there's other ways of getting the convex hull. This is just what I came up with. And so we start off with 0 and 1 as our convex hull, the first two. So I have these in my stack. And then I add the next point to the stack, which is 2. And so now this is my convex hull. And I don't know yet if the other points are going to be inside here or what's going to happen. Then I go to 3 and I can see all of a sudden this angle here has changed, or the rise over the run has changed from this line to this line. And so I'm going to pop 2 out of the stack because I know it can't be a 2. And then I will try to add 4 to the stack, but then the rise of the run is going the wrong way again. So I'll pop that and just add 4. So we just keep popping until we want a decreasing angle because we're or decreasing slope because we're kind of working out the outside here. So from 4 to 5, 5 to 6, it's slightly increasing, so we'll pop that. So 4 to 6, and then it's increasing again, so we'll pop that. And then we do something similar for the bottom, but we sort the other way around. So I guess you'd sort by negative y, I guess, and still sort by x, but yeah, you'd end up getting this half as well. And then we add the 2 halves to get our convex hull. Just a few things we have to be careful of is what if there's 2 points or multiple points on the line. We don't want to count these because they're still in the same half plane. So in my code, that's why I've got an equals sign here. So I just check the rise over run, and if it's the same as on the same line as before, then it's bad, and so I don't include it. The other thing you got to be careful of is, if the points are directly above each other, like you can see, like these three or like these two, it's like a vertical line, so then you get division by 0 if you're not careful. And I think they mentioned in the problem actually that there's one leftmost point and only one rightmost point, so you don't have to worry about the edge case of getting the leftmost and rightmost points. But otherwise you could have just manually found the minimum x and maximum x and just made sure you included all points that fit that criteria. So let's see our code here. So I'll go down to the main method. So we're just going through each case. We're reading some input, and we do this. I'm just doing this println, which doesn't go to standard out, which means I can kind of just track the progress to make sure it's going to run in time. Just reading all the points into this vector of points, and I'm calling this getHull method, and then I'm running Dijkstra's and printing out the answer. So let's look at this getHull method. So here I just sort the points, which by default just sorts by the first value and then the second value in the vector, so that's sorting by x and then by y. I'm starting my stack off with the first 2 points. Then from point 2 onwards, I just, I check the next point, is it bad? Like while the angle's bad, we just pop whatever's the last point in the stack, and then we finally add that current point that we're trying to add. So this is order n, but the algorithm's n log n because we're doing a sort here. And then I just sort by negative y here and just do the exact same thing again, except I'm just using this bad 2 function and this bad function, so they're just slightly different. Just sometimes you want the slope to go, well, the top half you want the slope to be decreasing, the bottom half you want the slope to be increasing, I think. So my hull is kind of, I guess it's potentially missing some values. Because of this equality sign, I'm missing some points from the convex hull, but that's what we want. And I'm also kind of taking into account there's only one leftmost point and one rightmost point. Okay. So here I'm starting from when I add to this is my output. So when I add from the top half and the bottom half, they both include the start and the end. So here I'm including the start but including the end. And then here I'm excluding the start but including the end. So I think all the points in my hull should be unique, and just the ones we care about. And then the Dijkstra's, so I've got the hull, and we've got a few parameters that are part of the problem. And we run Dijkstra's in n squared time rather than, we get rid of the log n factor because every point is connected to every other point potentially. We don't need a priority queue. So we just start off at the start, which is point 0, and once we get to the end, we just return whatever the distance is. So we're using dp to store the distance to each node, which just starts off at none for all of them, and we haven't explored from any nodes yet, so none of them are done. But then the distance to the start is just 0, and I set down 0 to true here. I don't think I even actually need that here because I'm setting it down here. Anyway, so so what are we doing? So we're starting off at 0, and for every other node that's not equal to 0 and that's not done, we just work out the cost to it, which is just the cost to the current node plus the distance squared, or the maximum of that in k. which is just part of the problem requirements. And then we just set the distance to j. So if we already have a distance to the jth node, then it's just going to be the minimum of its current cost and this cost. Otherwise you just set it, if it doesn't exist, we just set it to some cost. So now we've found all ways of going from node I to all the other nodes. So I is done and it can't contribute anymore. And then we want to look at the next closest node that hasn't been done and explore from that. And that way we're always doing things from nearest to the start onwards. So it's just the most efficient way. And it prevents requirement for recalculations and things. So here we're just finding, what's the closest distance that's not yet done. So we're just enumerating this done array, and this is pretty quick in Rust because then it doesn't need to do bounds checks, because that's one thing that's good about the borrow checker. It can guarantee nothing else is modifying this array at the same time. So this filter map is useful. It just returns an option and it filters out all the options that are none. So if it's not done, then we just take its distance. If it is there, we just map its distance to the distance and the index, because we actually are concerned about the index, and then we're just taking the minimum. So the minimum based on distance. And yeah, if we didn't find a minimum, then we just return -1. It's impossible to keep going. Otherwise, we just set I to the minimum index. And yeah, that's pretty much it. So it runs in about 20 seconds. There was an interesting problem. And there's just one other problem I did. I didn't do the first problem, but I did the one with the wells. So you have a bunch of wells everywhere, and you've got a bunch of trees, and you have to work out the sum of the squares of the distances between all the wells and all of the trees. So it's like, maybe like 1 million wells and 1 million trees or something like that. So for a given well x, it would just be like, you want x minus x1 squared plus x minus x2 squared, and so on. And then you also want y minus y1 squared plus ... But it's the same thing with the y's, so I'm not going to show that. And so x would be the location of a particular well, and x1 would be the x coordinate of tree 1. This would be the x coordinate of tree 2, and so on. So if you just expand that out, you get x squared plus x1 squared minus 2 times x1. And then for this second bit, you get x squared plus x2 squared minus 2 times x2. And if you rearrange that, you end up with n x squared, and then plus the sum of xi squared, so x1 squared, x2 squared, and so on. And then you get minus 2 times x times with the sum of all the xi's, which is just like this one and this one, and so on. You're just taking negative 2x as a common factor, so you're left with x1 plus x2 plus x3, and so on. So if we were to run this for every single well, it would be too slow because there's so many trees. You'd have a time complexity of like 1 million squared. But if you just pre-compute this sum and this sum, then you can just call this like, what will we call this? Sum squares and some x's or something like that, then yeah, this is an order 1 operation. So then the cost is just 1 million. So that was a pretty straightforward problem. Hope those of you that did it had fun. If not, try give the problems a try. I'll link to the problems and some of the code. And yeah, might see some of you in round 2. Good luck everyone. If you get top 2,000, you'll get a t-shirt, so that'll be cool. Alrighty, catch you later.